Hello and welcome to my video from chapter 3 and 4, lesson 5. This is called logarithmic functions. So we're looking at graphs of logarithms. Okay, so remember from our first unit, which was transformations, the inverse function? Well, inverse function is when this happens. So in the original function, we have f of x equals y, or y equals f of x. So y is some function of x. So for example, y equals square root of x. But what we're doing is we're switching the x and y position when we find the inverse. So for example, we go like this and we switch the x and y position. But we have to rearrange it. So we're going to have x squared equals y. So you're going to notice that x squared equals y is the inverse of y equals square root of x. So what happened is the x and y switched positions. Okay, so when that happens, we call this a reflection over the y equals x line, or we call it the inverse. Both are perfectly reasonable. We call it both ways. So it turns out that exponential functions and logarithmic functions are inverses of each other. So here is our original function here. This is our exponential function. And what we can do now is we can swap the x and y positions. So this would be x equals 10 to the y. And when this happens, to solve for y, there's only one way to do so, and that's using logarithms, because it's log base of the answer equals the exponent. And so now we have an expression, which normally we would just write as log x, because 10 is our default. And here is our expression that has been rearranged, i.e. they're inverses of each other. So that blue circled boxed one and the red boxed one are inverses of each other. The x and y have swapped positions. Okay, so what that means is we're going to follow the normal inverse function graphing rules. Okay, so first of all, what does that blue function look like? Well, at first we're going to have a dot at 1, and then when there's x equals 1, we're going to have a dot at 10, and then we're going to have a 10th, one dot before, and then it kind of just kind of have to draw it closer and closer without ever touching the x-axis. Something like that. Okay, so this is our original function, and what you're going to notice about it is that this function has an asymptote. Maybe I'll use, I'll just use orange. I'll do dotted. So it has an asymptote here at the x-axis line, i.e. it never touches the x-axis. Okay, so if we take that same function and we reflect it over the y equals x line, okay, that's what the y equals x line looks like. And if we reflect it over that line, we're going to end up having a dot over here, a dot over here, roughly, a dot over here, and then you can kind of continue the pattern from there. So it's just a question of being able to draw it nicely. So what we've done is we've reflected that line, and this, I didn't do 2x, I tried to do 10x, but whatever, it's the same sort of thing. So I just drew this. If it was 2x, it would just be spread out this way a little bit further, but whatever, you get the idea. So this one is log x. Okay, so here we have that function, and hopefully that makes some sense. It's being reflected, those are inverses of each other, and now you know what a logarithmic graph looks like. What do you notice about the asymptote of the two graphs? Well, hopefully you can notice that the log graph has this vertical asymptote instead of a horizontal one, and it's at a different location. So we're going to write down a few different things, but the most important thing is that asymptote. So x cannot equal 0 for the logarithmic function. I'll use color coordinate. X cannot equal 0. And then for the original exponential function, y cannot equal 0. Okay, for the original exponential function, we can say that the domain is in the real numbers. But we say that the range is greater than 0. So in comparison, the logarithmic function, the range is in the real numbers, and the domain is greater than 0. And this is simply because, again, it's the opposite. So the x and y positions have swapped. So if we think about the y-intercept, we would say that it's y equals 1 by default. And the x-intercept does not exist because it can't ever get to y equals 0. The logarithmic y-intercept does not exist now because, again, they've swapped positions, but the x-intercept is x equals 1. So in every sense of the word, they have swapped x and y positions. Okay, so with all that said, we understand some of the basics of the logarithmic functions, but let's take a look at some transformations. So there's different transformations that can occur, but the important thing is, what is x being replaced with? So x is being replaced with x minus c. Well, that means we're going c units to the right. Okay, if we deal with the d value, this would be y is turning into y minus d, because that d would move over to the other side for it to be replaced. So we're moving d units up. Okay, the b value. Individually, the b value is replacing, so it's multiplying by x. So that means that we're going to be saying, we'll use horizontal stretch by a factor of 1 over b. Okay, and then last but not least, y is being replaced with y over a, because you could divide the a over, and that means there's a vertical stretch by a factor of a. And also both of these could result in a vertical reflection or a horizontal reflection if you made one or both negative. Okay, so we're going to compare some actual results here. So first of all, we're going to compare that first one with the original. So the original is going to be 1, let's say 1/2, 1/4, 1/8, etc. This is going to end up being 2, 4, 8. Okay, so this is the original logarithm, base 2. Okay, that's the original, the OG. Okay, so if we're looking at log base 2 of x minus 4, what's happening? Well, x is being replaced with x minus 4, which means that it's just simply going to the right by 4. So we're going to try that right now. We're going to take all of these dots and move them to the right by 4. If we move this one to the right by 4, that's 2, 3, 4. And then this one will go to the right by 4, so this goes like here. And one of the things to consider is perhaps just consider drawing out the asymptote. I'm going to erase it afterwards, but just to keep in mind, like that asymptote moved to the right by 4. 1, 4. No, 1, 2, 3, 4. Oh, you know what? See, that's why you got to draw the asymptote. I didn't do it right the first time. Okay, this is going to show that actually it's going to be really tight here, but that's okay. I should have made it go to the left. Something like this. So this is what our function looks like. Okay, let's take a look at our next one. What has happened here? Well, y has been replaced with y plus 4, which means it's going down by 4. So we take all these points and we just go down by 4. 1, 2, 3, 4. Okay, so it doesn't change the left side that much. It just goes down by 4. And it'll look something like this. Somewhere around there. Okay, and if we compare with this one, which is kind of interesting, well, what's happening? It's that there's a horizontal stretch. Well, x is being replaced with x over 4, which means a horizontal stretch by 4. So horizontally, every point is being quadrupled. So if you look at no, it isn't quite doing what I thought, what I predicted. Let's go ahead and actually just try this in our calculator. Sometimes it's just fun to play around with it a little bit and see what's going to happen. So there's one of them, and now we're going to graph the other one, and we're going to compare them and see. Okay, so actually I think we want to just go a little bit further there. I think if we make that an 8. No. There you go. Okay, so those two are the same. And so actually I need to change something here. I need to make this a 16. Okay, so why is it that those two are the same? Well, because if we move down by 4, you can see that every single one of the points like kind of still exists, but if we stretch it, we times it by 16 in the horizontal direction, then we can get back to those original points. So, for example, this point here is at 1/2. This point here is at 8, right? Because this point was at 8, right? So if we take 1/2 times 16, it equals the 8 that we have over here. And we can do that for all of them. This is a quarter times by 16 equals 4, and that's what this point is. and you can keep going from there. So interesting to note that a horizontal stretch is the same as a vertical translation. It ends up being the same. And with that in mind, you don't need to, if you're being asked about a transformation, you don't need to have both, right? We don't need to pick one. Okay, let's try a different one here. Here we're going to use this one, and this is a vertical, well, hold on. Y is being replaced with y over 4, which means it's a vertical stretch by 4. Okay, so vertically it's being stretched by 4, so we're going to take every point, I mean, this one's not going to move, but every other point and quadruple it. So this point is going to be 1, 2, 3. Oh, whoops, 1, 2, 3, 4, somewhere around there. Oh no, quadruple it, not add 4. Yeah, okay, no, it's going to be right there. And this point is going to be somewhere around here. Okay, this point is at -1. So if we quadruple it, it's going to be down here. And this one's going to be somewhere down here. And, you know, you can't really be entirely perfect with this, but you can kind of see the rough shape of this. It still looks the same, except it's been stretched quite a bit. We're going to compare it to this one. You'll notice that this is not a transformation, but you'll notice that it looks a little different, and that's on purpose. So we're going to insert a 4 here on the outside. We're going to get rid of that 16, and then we're going to insert a exponent to the 4 here and see how they look. Well, you should be able to see that they're, they look very, very similar, but actually I'm going to switch the order of those two. We're going to delete this guy and make this to the exponent 4. You might be able to see it more clearly if I do it this way. So here you can see the one version, and then the other version is just on this side. So that's interesting. What's happening? Well, because the inside of a log must be greater than 0, must be positive, this one needs to have that restriction. So x is greater than 0. But because the bottom one here has an exponent to the 4, x can actually be any real number. And this is because even if you have a negative in there, like -2, when you do it to the 4, you're going to end up with a positive result of, in this case, 16. So positive or negative gives you a positive result. In that case, the log works just fine. So interesting, they're the exact same except for that one little detail, the domain. Okay, so let's continue on to our last one. Here we have x being replaced with 4x. So it's a horizontal stretch by a factor of 1/4, which means everything's being compressed horizontally by 1/4. So this one turns into a 1/4. This one was at 2, so this one's a 1/2. This one was at 4, so this one's going to be at 1. This one was at 8, so it's going to be at 2. The next one would be at 16, so it's going to be at 4. And you might see a pattern here, maybe, and if not, hopefully it becomes a little bit more clear. As I draw it. And the pattern is, well, it just looks like the black one, but shifted up. Okay, so what does that look like? Well, I'm purposely drawing this other version of this because we already saw a vertical stretch. But here you can see that this one is just simply a number, right? So sometimes we could have, some sort of statement that doesn't look like it's a transformation, but it ends up being a transformation because this one here in blue is the same concept as in green. There's nothing really new happening here. And so, yeah, again, we can graph those, and we'll do that on our calculator just to compare the two. Okay, so that's our first one, and our second one looks like this. Okay, so there's our second one, and there's our first one, and they're perfectly overlapping, so they look actually the same. All right, I hope this video helps you better understand logarithmic functions and the transformations, the characteristics, and the fact that it's an inverse of an exponential. I hope the video helped, and good luck.